So I'm now delighted to welcome Nicole Coleman from Stanford University. She is leading an initiative there to identify and, I'm just going to put my glasses on, to identify and enact applications of artificial intelligence, machine perception, machine learning, machine reasoning, and language recognition, to make the collections there more easily discoverable, accessible, and analysable. So without further delay, I'm going to hand over to Nicole.
Thank you, Carolyn, and it's lovely to be able to be here. I was hoping to keep the presentation short enough that we could have questions. Of course, now we're 15 minutes into it, but I'll do my best to move rather quickly. So, as Carolyn said, I'm coming here from Stanford University, and I wanted to, as a sort of preamble to this talk, give a little bit of context of what that means for me. Stanford University, of course, near Palo Alto, Menlo Park, right there, kind of in the heart of Silicon Valley, and not to mention also, very, very much integrated in terms of research that comes out of Stanford and goes into the Valley. So my title, Act Deliberately and Preserve Things, is a response to this, Move Fast and Break Things, which, if you may be familiar with this is the motto of Facebook. And this is the Facebook CEO, Mark Zuckerberg, at a keynote address that he gave in 2014, when he decided to change the motto officially to move fast with stable infra, which is meant to, short for infrastructure. Now, so the context setting here is to talk about what I feel and experience sort of day to day as this rapid acceleration of AI and implementation of AI. And Facebook is generally considered an AI company, and to give you a kind of window into the thinking there, what Zuckerberg said at this keynote with this shift in the motto was, so today, for the first time, we're introducing a 2-year stability guarantee for all of our core APIs and platforms, including login and sharing. So this means that even if we change these core APIs in the future, we're guaranteeing that we're going to keep supporting them as is for at least 2 years, and maybe longer from the time that we make that change. I hope you would all agree that 2 years is just simply not enough for anything. Like Paul, who spoke this morning, I'm enthusiastic about the opportunities of AI if we, the libraries, become involved in what those changes actually look like. So more about AI, what it is and what it isn't. This is a quote from Ray Kurzweil, who is proponent of the singularity. Paul also mentioned this morning. I'm just going to read this to you. I like this quote because he's really focusing on AI as being part of information-based technologies. So within several decades, these information-based technologies will encompass all human knowledge and proficiency, including, ultimately, the pattern recognition powers, problem-solving skills, and emotional and moral intelligence of the human brain itself. This singularity will allow us to transcend the biological limitations of our bodies and our brains. We will gain power over our fates. Our mortality will be in our own hands. We will be able to live as long as we want, and we will be able to fully understand human thinking, and we'll be able to vastly expand and extend its reach. Okay, and then this is from the marketing materials for NVIDIA, which is maker of the GPU hardware that's significantly driving AI in the Valley. So artificial intelligence, the dream of computer scientists for over half a century, is no longer science fiction. And in the next few years, it will transform every industry. Where engines made us stronger and powered us in the first industrial revolution, AI will make us smarter and power the next. What will make this intelligent industrial revolution possible? A new computing model, GPU deep learning, that enables computers to learn from data and write software that is too complex for people to code. So people falling into the background. And then finally in this line, Elon Musk. This is from his Twitter feed where he tweeted this image and said, if you're not concerned about AI safety, you should be. There's vastly more risk than North Korea. If you're not familiar with this image, this is actually, in the end, the machines will win. It's a public service announcement for gambling. So that's part of the world in which I live. This is another part of it. Robert Harrison, who's professor in Italian literature at Stanford and runs a wonderful podcast called Entitled Opinions. He says about Kurzweil and sort of his ilk, these guys should all take 2 years out of their lives to undergo an education in literature, maybe scripture and the classics, and learn something about how to improve this really tacky imagination they have about what the good life is supposed to consist in. And then there's Douglas Hofstadter, and this speaks more directly to something I'll be showing you in a moment. If you look at situations in the world, they don't come framed, like a chess game or a Go game or something like that. He's referring to games, which were sort of landmark events in AI that sort of showed how intelligent computers are. A situation in the world is something that has no boundaries at all. You don't know what's in the situation and what's out of the situation. So this is a sort of key setup. I'm not defining artificial intelligence formally, but hopefully this gives you some sort of context. I will go so far as to say that, at least for the purposes of this talk, it's neither artificial nor intelligent. And I'm taking that from Fei-Fei Li, who is associate professor of computer science at Stanford. She's also director of the Stanford AI Lab and is also director of an initiative that is just getting started officially, I think actually in the fall of this year, that's called Human-Centered AI at Stanford. So she says, and she wrote this in an op-ed in the New York Times that was just published in March, despite its name, there's nothing artificial about this technology. It's made by humans, intended to behave like humans, and affects humans. Interesting there, that part about intended to behave like humans. That's a little bit scary to me. But Edward Feigenbaum, who is considered by many the father of expert systems, there are many, I picked him just because, he was at Stanford and we have an archive of his works there. But Ed Feigenbaum said, AI is essentially pattern matching within a very wide space of possibility, period. And that's kind of the crux of what we'll be doing. So meaning not intelligent, it's just that machines can search a lot much faster than we can. So AI touches our lives every day. Can anyone shout out some examples of the ways in which you interact with AI during the day? Don't be shy, people in this room. No, okay. Siri, thank you, Siri. So Siri, Alexa, Google, exactly. Google search is AI-driven. The spam filter in your email, any kind of recommendation systems, and our assistants, voice assistants. So all of these things grew out of a really small set of ideas, and now they've kind of grown into these really important areas of research, of robotics, natural language processing, computer vision, computational genomics, and medicine. And there are really three key things that have made this shift possible, and that's improvement in learning techniques, increased processing power, and also lots and lots of data. So first, to look at machine learning, and I want to really clarify it's actually training, it's not learning. We can look at this in the context of kind of like a timeline and the acceleration of things. I could have started in mid-last century, really, where some of these ideas were just getting started. But I decided to start here with 1986 because this paper that was published, or maybe it was an article in Nature on learning representations by backpropagating errors. If you're not familiar with backpropagation algorithm, it's kind of continues to be utterly relevant today in machine learning applications. So that's kind of the start of what I see as a really strong movement. But yet, you can see in this timeline, there's still gaps. So, this, in 1989, then Jan LeCun applies deep learning to reading handwritten zip codes on envelopes. That is something we'll actually take a look at that. It's the same technology that allows you to, take a snapshot of a check and send it to your bank through your smartphone, if you do that sort of thing. then in 1997 is one of these landmark events that I mentioned, and it was IBM's Deep Blue beating Garry Kasparov at chess. Right? What's significant about that, I think, is that it started a kind of excitement about the potential of AI. But like Douglas Hofstadter said in the quote I read before, it's a really narrowly framed problem set, chess, right? It's challenging for us as human beings, but Kasparov is, considered to be quite intelligent because of his ability to play. But for a computer, because it follows a very strict set of rules, it's pretty easy. In fact, in some ways, you needed a lot of processing power, but to consider all of the different possibilities and just sort of be able to select really quickly and rapidly what would be the ideal next move in order to achieve the ideal result. So it's very impressive, but it certainly isn't intelligence. Okay, and then 1998 has a kind of point for us, Larry Page and Sergey Brin founding Google, which was based on the PageRank algorithm. So at that time, PageRank algorithm, certainly consider that AI, but it's not deep learning. This is early stages. And then if we move to this next period, 2010 to 2016, so really just in the last 6 years, there's been this more rapid advance. And here, because I'm talking about learning techniques, I'm really sort of focused on how deep learning, I've selected events that are particularly about deep learning, right? So in 2010, there was a paper on deep learning for speech recognition by George Dahl. So that is exactly what some of you were mentioning. That's what has made Siri, Alexa, those kind of assistants possible. And then in 2012, Jeff Hinton, who was advisor for George Dahl, published another paper on deep learning for computer vision using something called ImageNet, and we'll come back to that. At the same time, Andrew Ng, who's now adjunct professor at Stanford and runs one of the machine learning labs there, his team applied unsupervised learning examples on cat videos. And again, I'm going to come back to that and explain unsupervised versus supervised. But interesting, as I was talking about that connection between Stanford and the Valley, Google hired Jeffrey Hinton only 2 years after that, or 1 year after that deep learning paper. And then Dahl also joined Google Brain in 2015. And Google Rank Brain, which you might not have noticed any difference, but that became the new way of doing search, Google search, and it's using deep learning techniques. Now, the last point there being Google's AlphaGo defeating Lee Sedol. So it's defeating the world champion of this game, Go, which was considered a major landmark because unlike chess, Go has an almost infinite number of possibilities of ways to play. So the distinction there was that unlike Deep Blue, AlphaGo wasn't fed all of the rules. It was reinforcement learning, a particular kind of learning technique that was used, which is rewards-based. And so maybe an easy way to explain it is AlphaGo basically kind of played itself many times and learned the game. Not by an explicit set of instructions, but by being rewarded for success. So it knew what was a successful move and whatnot. So interestingly, the math to accomplish that is nothing really more than 5th grade algebra. But the fact is, again, it's being able to make those calculations in a tremendous number of times, with great speed. But it's not intelligence insofar as it's not general intelligence, right? AlphaGo cannot do anything else but play Go. That's it. Okay. So that big shift, as I mentioned, in these recent years, and just the last 6 years ago, is deep learning, and that deep learning we can learn in an unsupervised way or a supervised way. So supervised meaning we give some training examples in order to kind of train the machine what we want to achieve. Unsupervised was a dramatic development, and that's right there in 2012. Andrew Ng's team applies unsupervised learning on cat videos. What that means is essentially I've got so much data. Andrew Ng refers to it as, you need, for supervised training, you need a lot of data. For unsupervised training, you need almost an infinite amount of data. And the idea is that by simply throwing it out and letting the machine do its own classification, you don't need to tell it first, find this, I'm looking for cat, so I'm going to show you, yes, this is a cat. No, this is not a cat. It doesn't have to do that. It just says, look at all of this stuff and start to classify it. Now when I hand you a picture of a cat, you can find something else that matches that, right? That's close enough to match that. I hope that is pretty clear. Okay, so the second big thing, processing power. So same timeline, 1999, NVIDIA developed the GPU, which, unlike CPU, it's graphics card. As you recall, this is really for gaming, right? Lots of fast rendering of visuals on the screen that required parallel processing, a lot more processing power than we had with standard CPUs. So it might be that nobody really cares about that except NVIDIA, but what it led to later then was Andrew Ng, he started using NVIDIA GPUs for deep learning. So the deep learning work that he did with those cat videos was done with Google Brain, where Google has an infinite amount of money and effort and resources to be able to pour into this. This was distinctly different because it was able to be done on, with GPUs costing only about $100,000 instead of $1 billion. And this came about in part because they had this great success with the cat videos, which sounds ridiculous. But and Andrew Ng said he was excited to share this with his students, but they were saying, look, I don't have 1,000 computers lying around, so how can I pursue this research? All right, so this was actually, the hardware was a major, major breakthrough. And just to give that some context, these are some numbers from Ben Vigoda at MIT. This idea of 1 million microchips equaling the compute power of the human brain at the cost of $1 billion. Okay, so that's like Google Brain. He says, by 2026, it'll take only 10,000 chips at a cost of 10 million. In 2036, only 100,000. Then by 2046, it'll be one chip at a cost of $1,000. Now, the point here being, it is going to become more and more accessible. Whether it follows this kind of trajectory or not, it's something that we will have to not only have to grapple with, but we'll actually have the opportunity, right? More likely to actually do some significant kind of computing work. And we can assume that that's going to transform significantly how we do our work. So the third point, lots of data. So this is, again, I didn't realize I had so many quotes here from Andrew Ng. He says, it's not about who has the better algorithm anymore. It's really about who has more data. So here I hope you can see it at the red at the top there, now of the same timeline I just pulled out. In 2005, Amazon launches the Mechanical Turk. That's somewhat significant, particularly for ImageNet, but basically, Mechanical Turk is a crowdsourcing tool. So it's a wonderful way to distribute work, but it's also a really great way to gather a lot of data. And ImageNet is a database of images that was set up by Fei-Fei Li and other of her colleagues, specifically to create a kind of open, shared data set that researchers could use to do some of this work. Because, as I described, supervised learning is a primary approach to machine learning, they needed labeled images. It is very difficult to gather a really large collection of labeled images. But what she did is they had Amazon Turk workers actually do the labeling. Okay, and so then we look at, again, in more recent years, just a couple of added points here. So that deep learning for computer vision that Geoffrey Hinton successfully achieved was using ImageNet, right? So there's a success where ImageNet, because it was available, because we had data actually available, where he wasn't with Google, he didn't have the benefit of any of Google's assets, he could now achieve this new research goal, right? And then in 2014, Facebook launched the Newswire app, which has been much in the news, and also acquired WhatsApp. which is the smartphone assistant. That's simply to say you can sort of also imagine filling in. There has just been so much data gathering of our own data, which is contributing to this work. Now, I want to just have this little note here about ImageNet. This is interesting. It's from their website in their FAQs. Does ImageNet own the images? Can I download the images? No, it doesn't own the copyright of the images. It only provides thumbnails and URLs of images. So keep that in mind. We need to be building data sets and preserving data sets. ImageNet is not a librarian, is not doing that. Okay, so let's look quickly at how this, in fact, works. I realize that it's late in the day, and I guess, CO2 levels are high, people are tired. But just bear with me. I'm not going to expect you to understand this completely if you don't already. But really what I want you to get from this image is, this is a neural network, a deep neural network, or at least it's a picture, a graphic representation of one. And if you look at the images across the bottom, sort of showing these different layers, my point here is to show you that if you want to take a photograph, like in this case, we're doing facial recognition. You want to recognize this woman, find another different photograph of her. What the machine is having to do in that process is actually totally disaggregate the image, break it down essentially to pixels, but then, to edges. So I'll show you a bit of what that looks like with the context of this. So again, it's just an image, right? You can even see the pixels here of this set of numbers. The same concept as with the photograph of the woman's face. But this is one of these things where, we can easily read what these numbers are. Very difficult for a machine to try to read what those numbers are. But this is exactly the kind of work that Jan LeCun did, as I mentioned before, in the late 80s. Okay, so if we had a data set that had a whole bunch of different, unique, handwritten numbers, what we could do is, take, and here I just highlighted the fours, and if we set this apart, we've got a training set. These are some examples of fours. Some examples of all those different numbers. I want you to be able to find other numbers that are like that. And here I'm going to play, if we're successful, a really quick video tutorial that just sort of shows you how that neural network actually operates. It's helpful to see
with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. The network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents.
Okay, everybody got it? I can skip this. I'm going to move on. But so again, if the only thing that you remember here in this process, I just wanted you to basically see how the idea is you're taking an image, something we think of as a cohesive concept, and just breaking it down to numbers, right? Numbers and then weights that act upon those numbers. That breaking down is a kind of key point. Okay, so what are the results of it? So, I mean, I'm showing you this for images, but really the concept is very similar whether you're working with text or audio or images. And the results are quite profound. Here's an example. So, coming after in 2016, Stefan Ehrman at Stanford worked on this project where they used satellite imagery and were able to essentially map poverty, to look at crop distribution, that sort of thing. Also, there's another Stanford algorithm from the Stanford Machine Learning Lab where they determined that they could diagnose pneumonia better than radiologists, and I'm sure that this has been very much in the news, and identifying benign versus malignant skin lesions and that sort of thing. And once again, it's not because the machine is intelligent, but because it's able to process the information so quickly. So the idea, my point here being that this kind of concept of pattern matching can be applied to so many, many different things. We've seen, examples of the self-driving car. Here's LeBron James sitting in the back of the car, which has got all kinds of other problems that I won't go into now. But also things like this.
Audio as input.
It's been less than a week since the deadliest mass shooting in American history.
Our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
Especially our friends who are lesbian, gay, bisexual, or transgender. I visited with the families of many of the victims on Thursday, and one thing I told them is that they're not alone.
That's one project. This is another project. There's no audio for this one, but just so you see what's going on. So in the first case, they're taking audio and they're able to modify a video to make it look like he's saying something he said before. And in this case, they're actually modifying the video based on what this actor, his facial expressions, right? Yeah, it's very creepy. And not only that, but in the case of Obama, that was previously recorded audio, but Baidu just announced this thing just recently, right, March. The software can clone anyone's voice with just 3 seconds of audio. It's frightening. Okay, and so now on to what are the limitations of this. And here, I want to get into a little bit this issue about the language itself. So this is John Malinsky, also at Stanford, Graduate School of Education. He says, the danger I see with machine learning is that it gives rise to the qualified backformation human learning, for which machine learning does not bode particularly well. And the really good studies have been done that show that the language matters. And so despite the fact that engineers certainly know that the machine is not really learning. I mean, some may think, Kurzweil might think it is. But words matter. They have meaning, right? They capture the imagination, and they also have consequences. So if we continue to confuse machine learning with the kind of learning that humans do, it can lead to problems like we've had in the US, where we're treating K through 12 education like an engineering problem rather than a human problem, okay? So, or using student test scores as a proxy for teacher effectiveness. This kind of thing has been documented really well by people like Cathy O'Neill in Weapons of Math Destruction, looking at big data and the dangers of algorithms with bias. This is Herbert Dreyfus talking about what expertise consists in being able to respond to relevant facts, which is something very different than what computers do. But let me give you a little break. I'm going to show you an image of some birds for a moment, and I want you to tell me how many birds you see. 8, 7, 12, okay. So it's pretty close. 8 was the right number. But the fact that we actually have any idea at all how many birds were on that screen is really part of what makes us human. This is taking a perspective from neuroscience, because a computer can count the number of birds in that picture, of course, but it can't estimate the number based on intuition, right? So it can count them also really, really quickly, more quickly perhaps than, than we could look at it. But our intuition is based in our capacity for abstraction, and that really is in general intelligence. So that's just to, give you a break. Okay, bias. This paper was submitted by Mustafa Sisse and Pierre Stuck, who are both with Facebook AI Research, also known as FAIR. And what they were doing is they're studying, looking at bias detection. And among the images, I decided to use Obama again. This is one of the images that they used. And so they were looking, using ImageNet, and trying to see if they can label this image, right? So like if you wanted a caption for this image, can we automate that process based on ImageNet? So based on a collection of images and also the labels that have already been created, as I said before, by mechanical Turk workers. So that's human beings, could be any of you. And this is the label that this image came back with. Now, it's interesting outcome. So Mustafa Sisse, researcher from Senegal, said that we thought the problem was that the class basketball only contained pictures of black people. But no, the class contains just as many pictures of white people as black people, right? So basketball, just as many white players as black players. The bias is because black people are underrepresented in the data set as a whole, right? So this is a reflection of the bias within our society. It's a reflection of bias on so many different levels. But it's also part of the problem of the fact that we're working with data sets, or the engineers are working with data sets that are completely uncurated. It brings up a number of issues in terms of limitation. First of all, bias is not recognized until it's too late, right? In this case, it might not be too serious, but there are cases in which the implications are very, very serious. As I said, the data that we're using for training it's either not properly understood, right, because it doesn't have context, or it's just not properly curated at all. And the predictions then that come as a result of analyzing this data are based on prior behavior, right? I mean, we're looking at the past in order to predict the future, except without an awareness of really the past, like a notion of historicity with these images. So this project, machine bias, was done by ProPublica, and it's looking at a company that operated in the US that was predicting recidivism, and it was completely biased. This is an important point for me here, is that this was done by journalists. There's an effort within Stanford University and the journalism department to get the library to be a collector of data, precisely because journalists are going to need to have access to the data, and access to the data is a big problem. But if we're going to prevent problems like this, that's what we have to do if we're going to criticize the system. Another related point, so this is Timnit Gebru, she was at Stanford and now with the group Fairness, Accountability, Transparency, and Ethics at Microsoft Research in New York. This paper, I think it's not even, it's still in draft version, but it's been a really hot topic recently, data sheets for data sets. Essentially what she's saying is, let's kind of put into practice a way to understand, to have people document what's the data, what's its provenance, where it's coming from, what's the bias within the data. This is exactly the kind of thing that I'd like to see us be able to integrate within the library. We should be able to match, we should require data sheets for data sets, right, and have a system that handles that. So, fortunately, there is a lot of good work being done looking at algorithmic bias. There's the Algorithmic Justice Group, Black and AI, AI Now, which is a policy group in New York City. And then the book I mentioned before, Weapons of Math Destruction by Cathy O'Neill, another really great book that just recently came out. by Meredith Broussard is artificial unintelligence. Another paper, Closing the AI Knowledge Gap. What I like about this is with this paper, they're acknowledging the fact that AI researchers employ not only the scientific method, but also methodology from mathematics and engineering. However, the use of the scientific method, specifically hypothesis testing, in AI is typically conducted in service of engineering objectives, right? So this is to say, it's not that they're doing anything wrong. It's to say that it's time for us to really get involved and engage. So this is when I come to the role of the library. So this quote, we have the capability, now we need to know what questions to ask, is from Peter Norvig, who's the director of research at Google. He came and visited us recently, and that's what he talked about, and I thought, oh, we're the libraries, we have the questions and we have the answers. So Norvig says engineers need to become more like natural scientists. The task is no longer bug fixing, but observing and guiding, right? So it's a really different practice. And I think I'm hoping, this is a shift away from engineering as a dominant mode of thinking about how we do things. And Andrea Ng himself also says applications of AI are not engineering problems as much as they are subject matter expert problems, right? So we need to really bring it into the library, not hire it out, not wait for applications to be built for us. So as I mentioned, I think of this as a paradigm shift from engineering to design, and then it's up for us. We curate, catalog, preserve, and share knowledge. Working with machines in this way, I found this in the research that I've done, reveals the ways in which we take for granted how we actually contextualize that information and the value that that provides. I think that this increase in data and new structures for dissemination of data that are inevitable within the library are going to require us to move beyond a basic kind of keyword search to much more richer kind of contextual search, which is going to require AI. So it's not just about AI and having machine learning experts, it's about having information designers and data scientists. Okay, so if we look at discovery, I know that we're running, okay, good. Okay, so I hope it's clear at this point, AI, at least in the way I'm discussing it, is essentially search, right? So we're better to employ AI than within the library. We can think about applying it to learning how experts search within our systems, so we can optimize search in an academic context. The other thing with regard to discovery is, so I've been interviewing a number of our faculty and the bibliographers, curators within the library, and what we're finding is that for many students, as researchers, the library is really just a computing interface, right? It's becoming an online catalog, mostly. But what that means is what's not digitized and electronically cataloged is lost. As our technologies focus on the future, we're leaving the past in the dark. One of our librarians recently gave a talk where she discussed working with student researchers, and she said, okay, where do we start with search? And they said Google. She said, we didn't give Google everything. We need to start uncovering the materials that we have that aren't discoverable within the context of Google. So one of the structures for getting there, link data. I'm arguing that what AI offers us in terms of automation is a tremendous support for this move to link data as a model. And this is Philip Scurf, again from Stanford, who wrote recently about linked data having the potential to revolutionize the academic world of information creation and exchange. The basic tenets of what libraries collect, how they organize, and how they provide information will be questioned and rethought. Limited pools of bibliographic records for information resources will be enhanced by data captured at creation. Underline that. I should have made that one bold. By harvesting the entire output of the academy, an immensely rich web of data will be created that will liberate research and teaching from the limited, disconnected silos of information that they are dependent upon today. And I would say that this is not just about, this is a an exciting new model. Yes, it's destabilizing to not be able to think in terms of fixed and finite records, but kind of nodes of information that are constantly being, maybe not constantly, but that are able to be updated. But this is also really consistent with how our researchers are thinking about the work that they're producing. If we think about examples that Caroline gave of DH practices, where do these projects begin and end? If they're born digital, they can continue to evolve potentially, right? We have to have systems that allow us to be able to manage these. Ian Hodder, an archaeologist at Stanford, is really devoted to the notion of the living archive, right? It's something that is preserved, but not preserved meaning wrapped up and put on in a box somewhere on a shelf, but something that he can continue to do research on, that after he moves on, his students can continue to work on. Okay, preservation. So much of this new research that's being produced, like I was saying, is taking the form of data. And that's because, this is how researchers are making use of artificial intelligence. They're actually using machine learning to start to extract data. Now, what are we going to do with that? What does that mean now as something that we need to preserve? What form should we use, and what does it mean to preserve in this new digital era? It's an opportunity for libraries to start thinking about adopting new preservation strategies. This is something we've been thinking about a lot at Stanford in a relationship that we have with Stanford University Press, a Mellon-funded project to look at digital, full-length, peer-reviewed digital, we're calling them interactive scholarly works, but essentially books that are not e-books, but really brand new forms of scholarship. But they don't operate at all like a book, so it's a really different model. Okay, so in terms of preservation, 10 years is not enough. If Mark Zuckerberg was talking about 2 years. So there's a new, this is human-centered AI initiative at Stanford. There's also a data science initiative. And I was there at this inaugural meeting we had just a week or two ago. Marco Pavone, professor at Stanford, was presenting some of the research that his team has been doing around self-driving cars. And we've been hearing about all of the problems with self-driving cars. If we're going to be able to test and understand what went wrong and what didn't, we're going to have to be able to analyze and go back and reproduce the research and look at it and uncover problems. But when I asked him and all of the other researchers on his panel about data preservation practices, they said that the funding body funding this work requires us to store it for 10 years. So we're going to keep it for 10 years. And I thought, okay, what happens in year 11? And here's an example of another project where we've got a researcher, Dusty Schroeder, who is in Stanford. He leads the Stanford Radioglaciology lab. And he's looking at data about the ice, the depth of the ice sheet in Antarctica based on radar film, 35 millimeter film that was shot in the 60s and 70s, right? So an example of when we need to look back at old data to produce new research. This was 50 years ago, a team of scientists, they crisscrossed Antarctica by plane, this plane in particular, and they were collecting radar images of the ice sheets. It took about a decade to do this. This was like late 60s into the early 70s. And what they're doing is they're penetrating the ice and looking down about 3 miles. And those are measurements that are relative today, but problem being that this was in 35 millimeter film at Cambridge. So what Dusty Schroeder did is he went and bought a film digitizing machine in Hollywood, put it on the plane next to him, came to Cambridge, got an art historian to work with him and start to digitize this film. And the results of that are really significant. As you can imagine, the film is really fragile, but on the left kind of shows you an idea of the area that they covered. the published film record is on top. So that's what was published initially. And then this is an example of what Dusty has been able to accomplish with a high-resolution scan. And there's a lot more data, is essentially the point, right? So to make sense of the digitized, so he did the digitization process, but to make sense of this digitized radar data, Schroeder collaborated with Stanford computer scientists who applied computer vision and machine learning, these techniques that we are now all familiar with, to automatically read and record the key numbers on the scanned film images. The numbers represented information about the configuration of the radar antennas and timestamps of the flights that, when paired with the scientists' handwritten logs, yielded valuable latitude and longitude information. John Emmons, who's CS computer science doctoral student at Stanford, he was the one who developed this program to read or guess what number a digit represented, even when the digit was on film that had been flipped upside down or reversed or partially obscured by adhesive tape. Okay, so it gives you an example of the kinds of things that we could be doing to move our analog data held within the library into the digital realm to make it discoverable and available to more research. Okay, and then this is the last section, curation. Okay. What I want to talk about here is, so how might we learn from pioneer researchers like Dusty Schroeder to think about improving our own data extraction and dissemination services and build systems to preserve these new digital objects, right? So if we're extracting the data, so for example, we have a collection of maps and we want to be able to automatically, in the digitization process, extract data from those maps. What's the projection? What's the extent? The bounding box, that kind of thing, or even features within the map, we then need to be able to store that data. So I want to put this in the context of, this is the op-ed that Fei Li submitted to New York Times that I mentioned recently, related to this human-centered AI initiative at Stanford. So she explains the goals of human-centered AI. The first is that AI needs to reflect more of the depth that characterizes our own intelligence. Consider the richness of human visual perception. It's complex and deeply contextual, and naturally balances our awareness of the obvious with a sensitivity to nuance. By comparison, machine perception remains strikingly narrow, right? So she wants to improve machine perception. And to do this, she's suggesting we need to collaborate more with neuroscientists and cognitive scientists. The second point is that of this human-centered AI initiative is that we should look at AI as something to enhance us, not replace us. And we also want to ensure that the development of this technology is guided at each step by concern for its effect on humans. And I would argue, in addition to that, that the key to human intelligence, the keys to human intelligence are not just in looking at neuroscience and not just looking at the kind of mechanistic ways that our brains operate, but also to be found in how we organize knowledge, how scholars connect their own ideas to the past and to their contemporaries, right, through like citation networks and that sort of thing. The library holds this information, and we can operationalize it in the context, in the design of better systems of discovery that provide meaningful context for information. Thank you. Take questions that here. Yeah.
Yes, do. Thank you. Thank you, Nicole. That was fantastic. Really, really fascinating. We're running a little over time, but we do have time for questions if anyone has any questions from the floor.
Could you please tell us a little bit more about how libraries can work with cognitive scientists or neurologists? I'm thinking of George Lakoff, for example, and how we can apply their work to what we're doing.
Oh, well, that's an interesting thought. I wasn't thinking about libraries work. I'm really thinking more about, libraries working with primary patrons, humanists, social scientists, because what I'm saying is that there's an applied intelligence in the way that we work, the way that researchers do their work, that we can learn from. I think that I don't know. That would be something interesting to explore. But clearly, within computer science, they're seeing the need as we want to develop these models better, make them more flexible. We want to get closer and closer to how the human brain works. I mean, there's a whole camp of people who disagree that that's the way to go. And the example being, flight, right? That we don't model the way a bird, our planes don't flap like a bird. They soar. And so we don't necessarily want to try to replicate something, especially if we're looking for a technology that's going to enhance what we do, not something that's going to replace us.
I just wanted to ask a little bit about students and their understanding of AI. It seems to me, your very, very spooky Obama videos are incredibly creepy, but really important that students need to understand the possibilities of AI, both for good and bad. I don't know how far you've got in Stanford with that, or how much you feel that's a library-led responsibility.
Okay, I don't know if I would say necessarily library-led. I mean, I think that that depends entirely on the library and the organization of the library. But I certainly think that whether it's led or not, the library plays an absolutely essential role, right? I mean, the library plays a critical role, at least at Stanford, in teaching students how to do research. I've talked to so many faculty who say, teaching undergraduates, the notion of digital natives being really savvy about this stuff is absolutely false. They don't have a clue, right? So the way I look at it more is within the library, we need to strengthen our core. We need to strengthen the staff already doing the work, already experts in information discovery and information design and information management and information processing, and just understand what that means in the context of AI so then they can pass that on to students. But I think that's the best solution, and it's absolutely essential. I mean, I work mostly on the research side, so I don't have as much experience, but that's what I would think.
Any other questions for Nicole?
Thanks, Nicole. One of the barriers to entry to AI is having the data, which is why Facebook, Amazon, people are so prominent. Given that we all have data, but it's kind of siloed, kind of segregated, and it's not that big in the grand scheme of things, how much can we as libraries start to influence that and start to influence the development? And what hope is there of there being players coming into the market to look at uses of AI around library data, given that it's small, it's siloed, and the quality is frankly shocking sometimes?
Yeah, absolutely. Well, for one thing, I think that the need for, as I mentioned in the talk, this notion of infinite amounts of data that's not going to remain the case, right? I mean, there's a real explosion in supervised learning more than unsupervised learning, which requires more. But even within unsupervised learning, Jeff Hinton is working on different kinds of architectures that would actually make it possible to work with a lot less data. So I think that problem is going to be solved. And in fact, Andrew Ng was just speaking recently at a conference at the School of Medicine at Stanford, and he was talking about, you can get started relatively small. He was suggesting, collecting data, build an app, start to collect some data, and then you build on that and build on that. I mean, we have a lot more data probably than we realize. Within Stanford, we do have a problem of a huge catalog backlog, right? So we have a lot of digitized material, but too much that's not digitized, but we have a lot, but we don't have metadata for it, which makes it not useful for supervised learning because it needs to be labeled. So I think that one step would be to use machine learning to help us solve that problem, right? So for example, we have, this is kind of a funny thing, a collection of, I think it's something like 140,000 images of the Stanford band. They're digitized, fortunately, but we've got someone in metadata who's actually having to go through and catalog those images. And she was explaining to me the other day, because of our discovery system, after all the work that she's doing, you will still only go into the catalog and type in Stanford Band and you will get all of the images. In other words, there's no way to granularly discover them because they're all by the same author, you know. Well, what if we let her design machine learning algorithms to go through and find the features that are actually useful and would help make this material more discoverable. So, you know, I think it's kind of, let's use AI to help us. But I also think, you know, when I referred to this notion of strengthening the core, like we have to build capacity among the existing staff within the library. It can't be, well, it can be, but it's not, the solution isn't to hire new people necessarily.
Nicole, can I thank you again?
Oh,
It's been
thank you so much.
fascinating and great. And plenty for us to think about.